This video is about calculating the energy that's stored in springs, rubber bands when we stretch them. So just to get us started off, this is the key thing that you need to think about. If I've got a spring and I stretch it with a force F by an extension of delta L, the thought that might go through your mind is, oh, hang on a minute, I know about moving forces over distances. So you might imagine that as you stretch that spring, the work you've done is the force times the distance. So it might be F delta L. But if you're thinking like that, you need to think again, because the point is this force is not staying the same. So it was quite easy to stretch the spring at first, and it's got harder and harder and harder. Okay, so it's not actually the force times the distance moved, because this force is changing as you move it. So we need to look at that a little bit more carefully. To think about this more carefully, we do work when we stretch a spring, of course, because we're applying a force and we're moving that force, so we're doing work. And as long as we don't go past the elastic limit, the work done on the spring is equal to the energy stored. If we go past the elastic limit, we can't get energy back out of the spring, okay, because it's plastic deformation. But the work done is not the force times the extension, and the best way to look at that is from the graph. So what's happening is the force is getting bigger and bigger and bigger as the extension increases. So in the past, this graph would have been a flat line, because the force times the distance moved would have given you a rectangle. But now we've got a triangle. So this area here, the hashed area, is the energy that we've used in stretching the spring, which is the same thing as the amount of energy stored in the spring. Okay, so if we look at the maths of that, what we can say is, what is this area? Well, the most obvious thing, hopefully, is that that area is a half of the final force times the extension. So if it was a rectangle, it would be F delta L, but because it's a triangle, it's only a half F delta L. And we can take that a little bit further, because we know also the equation from Hooke's law is that the force is the spring constant times the extension. So what that gives us is a half times the spring constant times the extension, or a half K delta L squared. Okay, so two expressions here, both for the energy stored in the spring, okay, but one including F and one just based on the spring constant. Because, of course, as you extend it more, both of these two things are changing. So really the energy stored is proportional to the square of the extension. Okay, if we apply this to a rubber band, then it's not quite the same, because rubber bands do not stretch so that the extension is proportional to the force. A rubber band gives us a curve, and interestingly, due to the mechanism of how it stretches, as you load it, it goes up a curve like this, but as you take the load off, it doesn't reduce its extension to what you were expecting. So the loading and unloading curve for a rubber band is not like a spring, which just goes up and down a straight line. And that's quite interesting, because you can think about the energy that you put in and the energy that you get out, and those two things are not the same. Okay, so the way we get the energy on the loading part of this curve is to look at this blue area here. So this is the amount of work we have to do in stretching the rubber band, but this red area here is the energy we get out. So if, for example, you've got a catapult or something, you've put this much energy in, but you've only got this red amount of energy out. That means that you've lost some energy here. So this green area is the energy that's lost, and that normally goes to heating up the rubber. Okay, there isn't a nice simple mathematical equation for this. Okay, so if you get asked a question about this, the only way you're going to find this area is literally to count the squares. So you need to know how much each square is worth by doing a force times an extension, and then counting up the number of squares in between the two lines.